Hey guys, welcome back to the channel. So today is a very exciting day because we're finally going to be building our neural network from scratch. And yeah, just for a little bit of background, I've made a few videos that explain some of the concepts I'm going to be talking about. So I'm definitely going to be hand wavy about some stuff. And that's okay because I want to keep this video short, but I want to talk about the core concepts that connect everything together and then leave you guys with important topics that you can research on your own. And I feel like that's a good way for many folks to learn because I know if I tried to explain everything, the video will be too long and it might not even be the way that you guys need to hear it. So I prefer to talk about the stuff that's really important and the overall structure and allow you guys to take a deeper dive. So also one more thing to talk about before I get started is you don't need a degree or some crazy setup to run a neural network. And that's kind of the goal here. I want to show you guys how easy it is. I don't expect you guys to fully understand what I'm doing by the end of this video, but what I do expect is that you will have a lot more knowledge of how the process is, and then you'll be able to research things that didn't make sense more deeply on your own. So, without further ado, um, there's first the imports here, and so far in my experience of all these neural network stuff and things like that, I've been using these three libraries: Pytorch, um, Pandas, and NumPy. So PyTorch is what allows us to actually do this cool stuff with gradients and all that. And Pandas, as you know, is more, I guess, generalist, not just for machine learning. It's for data manipulation, and a lot of people use it, even if they don't do AI, they might use it for data engineering or um, things like that. And NumPy is actually I guess I would say a foundational library for pandas, because if you understand how NumPy works, then you can apply that to pandas and you're going to understand a lot of things like vectorization, which sounds scary, but it's really just applying some transformation or function to a bunch of elements or rows or whatever at the same time rather than having to iterate through a for loop. So I could talk a lot more about it, but I'm not going to just because that's not the focus of this video. But yeah, we use pandas to first read the train.csv file. And um, just for context, this train file is a Titanic data set from Kaggle. It basically shows you the data right here, what you see in this CSV file, but I want to turn it into a data frame so I can work with it and manipulate that data. And in case you're not familiar with your math, modes are the most commonly appearing uh, thing in your data. And we chose the most commonly appearing row, and that is displayed right here. So it looks like abbing Mr. Anthony. And just this is just a good practice, but in reality, every row is unique, so it didn't really matter. But I just did it anyways, just to show you guys what you would normally be doing, and then you would do that in order to handle missing values. And df.fillNA, think of it literally as a function to fill in the missing blanks with what we stored here in modes. And as you see here, we stored this, I guess you could think of it as a row, even though it doesn't look like a row, but think of the unique information as the row itself, and then these labels as indices for that row. I think if you're not familiar with pandas and you don't know what series are and stuff like that, it can look a little confusing. But yeah, just think of what you're seeing here as a row with identifiers. So anyways, I already showed you guys, but this is the data we see. So um, yeah, uh, I noted here that um, we have to normalize the data a bit. So if you look particularly at the fair, this number is quite a bit higher than the other numeric columns. For example, age is always going to probably be a bit smaller on average than the uh, fair, because the fair seems to be able to go up and down in terms of cost, whereas age seems a little more consistent. And you might be wondering, well, first of all, what does normalizing mean? And in this case, normalizing is uh, bringing it to a like kind of imagine squishing the values to a smaller, how should I say this, a smaller range. So an example, not in this case, but an example could be taking the log of a very big number or a series of numbers, and then they would all get squished between maybe like 0 and 1 or 1 and 10, whatever. And this is important because we don't want our model to think that the fair is more important as a feature than the age. Because if the numbers are too big for fair, then the model might think, hey, the fair is actually more important for predicting whether a passenger survived or not compared to the age, which is not true. So that's why we want to log everything. And um, you might be wondering, why is there a 1p? And I'm going to invite you to look that up if you're curious, but basically it's literally just adding +1 to the log function. And the reason for that is because if we don't add a 1, when you take the log of I think it's 0. I might be wrong. I'm talking from the top of my head right now, but I believe if you take the log of 0, it kind of causes some weird math. Um, so we always want to make sure that we do +1 so that we always get a predictable positive output between 0 to whatever the positive number is. So anyways, we did that. We made a new column called log fair, which is literally log +1 of the fair column. You can see that here. So you could see it kind of squished the values to a more reasonable, appropriate size for the model. And yeah, again, for us humans, it doesn't make sense, but for the model, we want to make sure there's no bias to any particular feature, also known as a column. So, um, obviously, there's also columns here that are completely not important for us to be able to make a prediction model. Like, for example, the name. Everyone's going to have a unique name, I would assume. So that's not going to help us predict whether a passenger survives or not by working with their name. So uh, I would say that it makes sense to only look at things that are numeric. And you might be thinking, well, sex isn't numeric, but we can translate it into, for example, 1 and 0, because it's a category. So basically, categorical data could be turned into numbers, but names, not really. I mean, if you tried to, it would be like one number for every row, and it would just doesn't make sense. It's ridiculous. So we gotta think of numbers or categories in this case. Um, so again, we have sex, we have P class right here, and then we have embarked. So again, those don't look like numbers, but we can kind of think of them as numbers if we turn them into categories. Imagine this. Imagine S turns into a 1, C turns into a 0, blah, blah, blah. Um, and I wish I had like a whiteboard or something and I could draw for you guys, but what we're going to do with these columns that I just talked about that aren't numbers yet, but we will turn them into numbers, is um, we're going to call get dummies on them. So the term that I want to invite you guys to look into, I'm not going to try too hard to talk about it because I think I could ramble on about it for a long time, but it's called one-hot encoding. So again, I wish I had a whiteboard, but for now, look here. Look how for the sex column, it made one hot encoding for sex female and sex male, and then it mapped it 0, 1, 1, 0, blah, blah, blah. And um, this this helps because the computer can read the numbers. It couldn't read male or female or whatever. So we had to map it to these two new columns. And you might be wondering, why not just have one numerical column, maybe just like a new sex column, sex number column, and then just map it as 0 to male, 1 to female. And the reason is because what if we were working with a column that had more than two categories? Like P class, as you can see, has three categories. We couldn't just do 0 or 1, 0, 1, 2. Um, or actually, I take that back. You might think, oh, why not do 0, 1, 2? And the reason for that would be that if we put all the numbers in one column, it would kind of close off the ability to manipulate the data as much. And I guess what I'm trying to say is that by separating each of these into different columns of 0 and 1, it's really fast lookup, very easy for the computer, but it does seem to be a little less obvious to us as the humans reading this. So at the end of the day, we're just making it easy for the computer to work with, or the model in this case. And um, there are other ways that you could model this data, like going back to what I was saying about the 0 and 1 in the same column or whatever, or 0, 1, 2. But that's that's a completely different topic. So I would invite you guys to just look up one hot encoding yourselves, and it'll all make sense what I'm saying once you have some context. Because right now it just seems pretty arbitrary. So so now that we got our new data frame with all these new columns, we have to um, define what those new columns are. So I did the added calls as the new columns. And then we did the features, and the features are now going to be everything that the model is going to pay attention to make its decisions. And look, we want to pay attention to age as it is, sibling, I think this stands for siblings. I might be wrong. And parch and stuff like that. I don't know what parch even means, but it's numeric, so I figured it could be useful for the computer to make a prediction. And uh, notice here how I'm no longer using the normal fair column. I'm now calling log fair as well as the added calls. So that's important because if I didn't specify what columns I want to use, the model might use the fair column, even though I explained to you guys why we wanted to squish it. So yeah, that being said, or moving on to the next thing, we have our dependent and independent variables. So dependent is like the actual answer, and that would be if they survived, 0 or 1. That's our answer. That's what we're trying to predict. So we don't want the model to see the t dep or dependent variable because that would literally be the answer. That's like giving a kid a test and then giving them the answer. So you don't want that. You want them to actually take the test and try to guess the best answers. So the independents are going to be those features that we just described. We're going to take those columns from the data frame. And you notice that both of these are wrapped in torch.tensor. And um, if you recall, the tensor is super important because it's going to have a computational graph, which means that it tracks the history of all operations that are done on those columns, which you should think of now as a matrix. And this is how it looks right here, tensor, and it's a bunch of numbers now. You see that it doesn't have any labels. You don't know the name of the column, whatever. And that's because the computer or the model doesn't care about the names. That's what us humans care about, not the model. The model just wants its numbers because that's how it works best. So um, if you don't know what a tensor is, you guys should watch my first video in this series, or you can alternatively just look it up. It's pretty important. I would recommend that if you're not familiar with this at all, be learn to understand the difference between a tensor and something like a data frame or a NumPy array. What makes a tensor special? And again, just in my opinion, one of the most important things is the computational graph. It allows us to see the history, and if we didn't have that, then we couldn't really learn, honestly. So now, next part is to normalize all the values between 0 and 1. And this kind of goes hand in hand with what I was saying about squishing. The model doesn't want to get overwhelmed by data that's too jumpy. And I don't know if that's the best word to say, but in real life, the price of the tickets could maybe be, I already forgot. I think it was like 20, $30 for the cheap end, and then maybe $70 for the more expensive end. That's a big jump. And the model could get confused by the jumpiness. Like imagine drawing a graph of those data points and then you connect the dots. It's going to be like very jagged. And we want to kind of smooth out those those peaks in the data and make it more flat. So that's going to help to by taking the maximum value of each independent column or independent variable and then dividing each of the rows in that column by the maximum value. And if you do that, you could just figure, like, for example, here, right here, the biggest value I see is 38. So we can divide each 22, 38, 26 each by 38. And that's going to help us keep the values between 0 and 1. Then here I just did the shape just to prove to you guys that we still have our all our rows, 891 rows, and then this 12 here is how many columns there is. And another way I want you guys to think of these columns now is that they're literally the features. They're the features of the model, and that's how many paths that we're gonna be considering, I guess you could think. So now we get to the fun part. Um, we are going to initialize our coefficients. And I think I talked about this block of code in my loss functions video, if I'm not mistaken. So I'm going to kind of breeze over this. But I just want to say that it's really mind-blowing that we're just completely randomly choosing numbers for our initial matrix. So we have n coefs, that's going to be how many features, so it would be 12 in our case. So we're going to literally just have 12, a row of 12 completely random numbers centered around 0, and that's why I subtracted 0.5, so it's centered around 0 instead of 0.5, because by default it randomizes between 0 and 1. And I explained why that's important to center around 0 in my other video, so I'm not going to go into detail, but it's just to make the model as neutral as possible when it's first initialized with its coefficients. And then requires grad is it's requiring the gradient. So it's turning the tracking on. Imagine, I guess you could think of it like turning your GPS on, keeping track of all the turns and stuff you did. So if we didn't do that, the tensor wouldn't be unlocking its full potential, and it kind of would be useless for our case. So next is actually calculating the predictions. And this is the crazy part. This is so simple, but so important. It's that we're literally just going to multiply our independence. If you remember, I think it was the variable is called t underscore indip or something like that. And then we multiply it by our coefficients. And those are those 12 numbers. And if you don't know matrix multiplication, go back to my tensor video. I did a very brief but nice overview. I had a visualization tool to show you what it looks like for those unfamiliar with it. But by multiplying it, by multiplying these coefficients, we're going to multiply these random numbers by all of the numbers in our independent variable matrix. And then along axis 1, which is the how should I say it? The rows, I believe. No, no, sorry. Axis 1 is the columns. So that's the y-axis. So we're going to sum up each column. We're going to basically imagine collapsing it into a single row now. So now after this function, this calcpreds function executes, it's going to return a tensor with 12 numbers. So I think like you could think of it as one row, 12 columns. So next, so that was our forward pass, by the way. That's one more that's one more important buzzword I want you guys to know about. So forward pass is when we're passing our data through our network. And next we have to do a backward pass. And again, if you watched my other videos, you would kind of have an idea of what that is. But um, just as a quick recap, backward pass means that we're going backwards in our computational graph of the tensor and seeing what went wrong and how we can adjust the weights or the coefficients, you could say, in order to get better and better little by little. So in this calc loss function, which is the backwards function, is or not the backwards function itself, but it comes hand in hand with the backward function, which we will see soon. Um, is we first calculate the prediction, calling this previous function, and then we simply subtract our prediction, or sorry, we subtract the dependent variable from our predictions. And the reason for that is we want to see how well our prediction was compared to the actual results. So we want to see, did our prediction of whether they survived or not match up with what was reality? And I I did make a mistake here. I want to backtrack to the calcpreds really quick. I said that we collapsed each column, but in reality, I should have said that we collapsed each row into a single value. So I apologize for that, but yeah, we collapsed each row, which represents a single passenger, collapsed into a single value, and then we would have like 800 something um, collapsed values, and then we would compare that to the actual dependent row, which is the survived row, and we would so by subtracting them, it's going to give us the difference, and then we do a mean to find the average, and then on average we would get a single number of how well our model performed in reality. And again, notice that um, both preds and deps were tensors. So you might think, based on what I just said, we would get a single lost number. But remember, don't think of this like just as a scalar number, but think of it as a single value wrapped in a tensor, and this tensor has a whole history attached to it of everything that happened to it in order to get to where it is now. So that's a lot to take in, but hopefully seeing the model, this model training cell might kind of wrap it all together. So we have epochs, which means 30 iterations, and yeah, epoch literally means one training cycle. So we have 30 epochs, it means we have 30 training cycles, and then learning rate is how fast it will learn. Covered all of that in my previous videos, so I'm not going to go too much into detail. And yeah, for our coefficients, we always want to make sure that it has the same compatible shape as our independent variables matrix. So in our case, what we've been talking about, it would be 12 since there's 12 features. And the reason I indexed 1 is because I want the columns, not the rows, because the shape, if you remember, is rows comma columns. So I want to get the column size so I can get 12 features. And then for each epoch, I'm going to calculate the loss. Remember, it's returning a tensor, not a scalar value. That was super confusing for me, so I keep repeating that. And the cool thing about a tensor is it can call dot backward. And you definitely couldn't do that with a normal Python integer um, or a pandas or a series numpy array, whatever have you. And yeah, that backward function is going to basically be the secret sauce to being able to find the optimal gradient to get better predictions. And it's going to store the result of the backward function in the dot grad property. So again, the backward function finds a more optimal way to um, decrease the loss, but it stores the result in the gradient property of that tensor. So you don't have to assign loss dot backward to a new variable or anything. Could be a bit confusing. And then here, I think this part's going to be a bit confusing for you guys, so I would highly recommend that you also look this up after I'm done speaking. But uh, basically, we want to not track the gradient anymore in this specific block of code, because the reason why is because when we update the gradient for the tensor, we don't want to remember the previous steps anymore. So I think I might have I might have talked about this a bit in another video, but I guess an analogy is would or a good analogy would be like if we had a GPS and then we took maybe like 100 steps forward, we wouldn't want to have the same directions we had 100 steps before anymore because we already moved 100 steps. So we want the GPS to update with new directions, not remember the old directions anymore. So that's why it's important to specify no grad so that it doesn't track this specific part anymore. And we multiply it by the learning rate because we don't want it to be too big. And I talked about why we don't want it to miss its mark. We want it to be slow and steady because slow and steady wins the race. And then after that, we want to zero out our history of what we just did right on the line above that. And that's the typical way that a training cycle might look like. I know it's a bit hand wavy. You could feel free to look it up if you'd like, but um, most likely you wouldn't have to do this unless you're a researcher or something. I just feel like it's great to see what the model is doing under the hood. So that's just how it might look. As you can see, the loss is going down lower and lower. It's getting better and better. And yeah, so that's it for a model right there. We made our first model. But the thing is, that was a linear model. It only had one layer, but a neural network is going to have multiple layers. So I'm going to be super hand wavy about this part here because this stuff is basically the same as the above, but we literally just introduced two layers instead of one. Of course, you could have many more layers, but I just wanted to get the point across. So look at that. Our first layer had has the same amount of, uh, I guess, features as as our input data itself. And don't worry too much about the syntax right now. Just focus on knowing that the first layer has a similar schema as your input data, but then layer two has only one column now. And the reason for that is that it's going to collapse the the data. So I have a picture here. It doesn't do justice because it's a lot more complex than our example. But look here. Look how the hidden layer L4 is a lot bigger than the output layer. And as you can see, it's the hidden L4 is getting collapsed. It's collapsing. Every node is connected to every other output L5 node, but yet it's collapsing. So we're doing the same thing here. We're collapsing the layers until we get that one single prediction number that we want um, for each customer. And another really important thing to know about these layers is that in each layer we can add an activation function. And I think that I put that in the calc preds function below, but basically an activation function allows the model to make nonlinear decisions now. Because before in our linear model, it could only literally make a linear decision. Like imagine in high school how you guys had like y equals mx plus b. That's basically the model's level of creativity. It can only make a line. But what if we want to make like a parabola or a way more complex function? We need more layers for that. And the activation functions help to introduce that nonlinearity. And as a matter of fact, they're actually essential, I would argue, because without them, if you had a bunch of layers without activation functions, all of those layers would collapse on each other and form a single big layer. And to understand that, I would really recommend looking that up because I don't think I'm able to explain it very well since I'm not a teacher myself. But it's really important to know that you need a activation function. And we have a lot of activation functions out there, but the two that I'm familiar with are ReLU, which literally all it does is it takes anything below zero and turns it into zero. And anything above zero remains as is, and that creates a piecewise function. I don't know too much about piecewise functions myself, but they definitely look pretty weird. See, they introduce nonlinearity. That's what happens when you use ReLU. And you also have Sigmoid, which is another activation function. I'm going to show you right here. So it basically, first of all, it's really helpful because it helps compress our output for the model, but it also pays a lot of attention, or I guess you could say it has a lot of weight for the values near zero. That has the most noise, whereas it kind of tapers out as the values get bigger, which is important because the model should pay the most attention to numbers that it's unsure about, and it can kind of ignore the numbers that are really loud. So I think I don't want to get too much into it, but the at symbol is just shorthand for matrix multiplication. And again, This is basically just a bunch of matrix multiplication. We're taking our independence, remember how we put that in a tensor, and then we're multiplying it by the coefficients in layer one, and then again, we're multiplying that result by layer two, and then we're also adding a bias. So a bias is another term that's again hard for me to explain. I don't feel like I could do it justice, so I would recommend you look up why we need a bias. But it helps to basically make the model not have to start from ground zero every time. And yeah, we're just squeezing it here. And then I'm gonna skip the loss part because that's the same thing we already covered, except it's optimized for multi-layers. So here, as you can see, it's pretty similar to our linear layer, except the only different thing is that we're we're iterating over the layers now as well. We're not just doing everything in one go per epoch, but in addition to looping through the epochs, we now are looping through each layer, finding the gradient for that layer, applying our learning rate, and then yeah, adjusting the coefficients for the layers that we're working with. Um, and this stuff here, it's not important to know really. It's just it's just a little bit more about how to split your data well. Um, and that's a video I can do in the future. But as a cliffhanger, I guess, for my next video in the future, I definitely want to talk about the importance of splitting because, as you know, computers aren't random. There's no such thing as randomness when it comes to computers. It's all pseudo-random. So we have to be careful because we don't want our model to start getting too cozy with the data and then starting to memorize it instead of trying to critically think, if you will. So yeah, that wraps it up for this video, and I hope that you guys got some stuff to take away. Again, just to reiterate, the goal wasn't to get you guys from zero to hero like a full course would. I mean, you'd have to have a way longer video to understand everything fully, but rather it was to kind of introduce a bunch of topics for you guys to be able to do a deeper dive later on. So I hope this helps, and without further ado, I'll see you guys next time. Bye bye.